All right, let's start then. So we are happy to be back for our second session of presentations. We had one presentation session and one panel. So we got to learn about industry side, demand side applications, and different aspects of deployed service and randomnesses. So next session, we'll have some more emerging trends in randomnesses, randomness generation in spatial settings, including stake-based setting, weighted VRF, Timelock encryption. You already also heard about the Timelock encryptions. And finally, using some sort of game theoretic fairness technique about randomness. The session will open with Arnab Roy's talk. Arnab Roy is a research scientist at Miston Lab, and he is going to present stake-based threshold random beacons. Arnab, please share the screen.
Can everybody see this?
Yes.
Let me try if slide mode works, but if not, I can come back to here. Okay. Okay.
Yeah, it's perfect.
Okay, awesome. All right, so thank you everyone for joining. And I'm going to talk about STROBE, which is the work that a bunch of us did when we were at Meta. I can see some of my co-authors on the call. Hi, Don, and also Costas is going to join for a panel later. So essentially, once we did this work at Meta, a lot of us moved along and hopefully are at better places right now. Okay, what is STROBE? STROBE is a random beacon. And if you didn't know what a random beacon is, it's a continuously operating application which outputs a random value at regular intervals. So STROBE brings some new properties of random beacons on the table, especially properties that are exciting and probably meaningful from especially a gaming perspective. So let me first dive into what are usual properties of random beacons, and then I can talk more formally about what new properties STROBE brings. Okay, so usual properties of random beacons that we want are, first of all, unpredictability. You don't want, for example, in a poker game to get a royal flush every time, or at least you don't want your opponent to do that. A random beacon should be unbiased. So it should output random values such that no individual or coalition can bias that output. It should ensure liveness, which means that the protocol should ensure outputs at regular intervals. And it should be publicly verifiable. So everybody should be able to undeniably attest to the fact that the outputs were legitimately constructed. Okay, so these are the usual properties of random beacons. There are some more, but I'm going to talk about some unique properties that STROBE brings. And especially consider gaming applications or applications where you may be in an internet constrained environment. Imagine you're sampling a random beacon at regular intervals with your mobile phone, doing some gaming. What if your internet connection is dodgy, or you're playing some high throughput game where you may not have the time to sample the randomness from the beacon every time? So what STROBE achieves are some interesting properties where the user can actually interpolate immediate values, even if they see snapshots at irregular intervals. Also, this as a corollary means that you can have storage efficiency of these random values. So it's not required to store all the beacon values. A sparser checkpointing can also allow efficient recall because you can store some of these checkpoints and reconstruct the values that are in the past. Okay, summarizing why STROBE, it brings unique streaming capabilities. It introduces this unique new property, which is perpetual history generation. From a current value of the beacon, you can generate past values of the beacon. And it also supports self-verification, which means that you can audit the values of the beacon with previous values without any expensive zero-knowledge operations. Okay, let's see how it works. So the key insight in STROBE is that pick a prime modulo any RSA number. The capital N here is a product of two primes, P times Q. And just ensure that U inverse exists modulo phi of N, which is not too hard. Now, let's say there is a designated entity which knows U inverse. Okay. If I know U inverse, I can start off with a random value X, which may be, for example, a blockchain hash. And then we can indefinitely keep computing x to the power 1 by u, x to the power of 1 by u squared, and so on. And what's a nice property about this sequence is that any public entity which knows u and not necessarily u inverse can verify this backwards. So any past value can be recomputed as the present value to the power u. And this can continue indefinitely, at least for an exponential time. Okay, so this is the key insight. There are lots of things to solve, even given this key insight. The person that knows U inverse is, of course, able to predict far in advance what the random beacon value is going to be in the future. Okay, let's first see what are the drawbacks of the key insights, the strawman so far. So how do we make sure that the setup generator does not cheat and the protocol does not stop if the dealer fails? So single point of failure, and we want to avoid centralization. Okay. And of course, what we can do is go to a threshold distributed setting. If we fix a number of parties N and a threshold T, such that we get the next two properties, which is that less than the threshold number of parties, even if they are colluding, cannot reconstruct the setup secrets, P, Q, and S. And if more than or equal to T parties remain live and honest, the protocol can keep making progress. Okay. The first one is decentralization, and the second one is ensuring liveness. Okay. To address trusted setup, we do have to use an MPC protocol to generate N and U so that we can prevent collusion. We don't talk about how to do these MPC protocols in the paper. It can be doable by generic MPCs, and there are also specialized protocols. But yeah, admittedly, this is not as efficient as DKG for elliptic curve based protocols. Okay. Let's see an example of how this protocol could work in a simpler setting. So the simpler setting is that forget about thresholds. It's just n for reconstruction and n minus 1 privacy. So we don't want n minus 1 parties to be able to reconstruct. And if n parties are alive, they can reconstruct. Okay. So what we can do is secret share this S, which is U inverse among n nodes, and essentially split S into random S1, S2 up to Sn, mod phi n, and give these secret shares to the n nodes, and observe that S is unpredictable to n minus 1 nodes. Okay. So let's see how the protocol proceeds. So let's start off with a random seed X. And then what each party does is raises X to the power of their share. And then when they combine that, they get X to the power of S. And this can go on. So then they take the next value X to the power S and then individually raise them to their secret shares. And again, when they combine those secret shares, they get X to the power S of S squared. And this can go on indefinitely. Now observe the interesting part about these secret shares. So each share can be checked with previous values as well. So if you look at, for example, the first one, X to the power S to the power S1, with the public value U, you can raise it to that public value U, and that cancels out the S. So you get X to the power S1. So each share can be checked against a previous share output of the previous epoch. And this holds for the final outputs as well. So this is what I meant by it has self-verification without any expensive zero-knowledge proofs. So this is a pretty unique property of STROBE versus other beacons. And this property is inherited from an earlier paper by Beaver and So, while being perpetual, which means that the Beaver So protocol, although it supported this kind of history generation, it was the number of iterations was needed to be fixed in advance. Whereas this protocol is perpetual, which means we don't need to fix in advance how many rounds it's going to go. Okay. And the zero knowledge free property is that with just an RS exponentiation, we can check current values against previous values. In fact, we can compute all the previous values with reasonable efficiency. The efficiency goes down with how deep you need to go. Some of you might recognize this as basically a VDF computation in the past. So that's how expensive it's going to look like. Okay. So that was like a full additive secret sharing. We can adapt this to K of n threshold setting as well using Shamir's secret shares. But a challenge arises for RS exponents because you cannot do fractions in RS exponents. Taking roots is hard in RSA groups. So we use a technique that was also used in Beaverso and subsequent other papers. So the observation was that if we multiply the exponents by n factorial, where n is the number of parties, then it clears out all the denominators and we have a nice integer polynomial in the exponent. So instead of computing F0, which is the usual Shamir secret sharing, we instead compute n factorial times F0. Okay, and we show in the paper how we can do that. Okay, so that's the construction. What do we prove about it? Security. So I'll just tell you about this as a game between a challenger and adversary. Essentially, it's like unpredictability. So how it proceeds is in a natural way. There is a challenger which generates the setup secrets, sends those. The adversary designates a few parties that it wants to corrupt. And it also sends a particular session or epoch that it wants to attack. Okay, and then the challenger generates a random X and iterates the generation of this random beacon for S epochs and also outputs the shares as well. And the adversary wins if it outputs the next number in the sequence. So if it outputs x to the power s to the power s plus 1, then it wins. Okay, and we prove in the paper that STROBE is secure in this model, given that the RSA problem is hard. So in summary, that was the STROBE random beacon. It has the usual properties of a random beacon. It's unpredictable, unbiased, live, verifiable. It can run indefinitely, at least for an exponential time. And it introduces new streaming capabilities like history generation, which is that it can compute previous values from any current value. So that's about it. Thank you for listening. And there's the link for the paper. Happy to take any questions.
Awesome. Great talk. Thanks a lot.
Thank you.
So yeah, it's pretty nice to see this stake-based randomness. I guess there are 3 questions. Arnab, can you read them out, or I can read them for you if whatever. I guess the first question is from Adin Tomiscu again. How well does the DKG MPC scale for this? I guess you mentioned that you run probably generic MPC you mentioned, right?
Yeah, so we have not implemented this, and definitely the DKG for this would be more expensive than an elliptic curve based DKG. There have been some work on generating RSA exponents without disclosing the prime factors to the shareholders. So distributed RSA exponent generation. Those may be better than generic MPC, but it's definitely at the moment not competitive with elliptic curve DKGs.
As a follow-up, is this same DKG, is it reusable? Can you use it for other applications?
Can you expand on that for a bit?
Use, for example, like this kind of standard, by standard I mean like group, like G to the X kind of DKG we can use for several like BLS or Schnorr or threshold encryptions. So this particular, I think you need to have this inverse, right? Is it specific or you use it? I know there is a RSA kind of DKG, but this is not exactly RSA, right? This is something different.
Yeah, the difference with RSA is that you need to generate that composite number in secret as the inverse of a certain prime number.
Inverse, yeah, exactly. So inverse generation might be the bottleneck actually. That's
So
what
you
I would
can't
say.
just grab some RSA exponent in the wild and use that.
So other question, how does this game-based security compare with real ideal simulation-based security? Are there any applications where the security is not sufficient?
Uh, yeah, so real ideal, I'm not sure about. I haven't thought about it, but this is one drawback of the security model is that it's adaptive. So the adversary actually tells the challenger that this is the epoch I'm going to attack at. A better security model would be like if the adversary can be adaptive and say that observe the beacon for some time and say that stop here, I'm going to predict the next one.
All right, I think there is another question you can see and maybe type the answer there. So I think we can move on to the next talk, which will be given by Sourav Das from UIUC. He is a grad student at UIUC, and he's behind one of the main authors of this distributed randomness using weighted VRFs. It's a very nice work. I did it at some point. And most importantly, it's already been deployed in Aptos. So it'd be very curious to know the technology and insights. Okay, so over to you.
You hear me well and also see my screen?
Yep.
Okay. Hi, everyone. I'm Sourav. Thank you, Pratyay and Aniket, for this invitation. And thank you for saying my name, how my parents would call me, Pratyay. It's in Bengali. Today, I'll talk about our paper called Distributed Randomness using weighted VRF. And this is a joint work with Deni, Ali, and Jolun from Aptos Lab. And this is already being deployed, as it says. And I'll talk about the cryptography behind what happens and also some of the design decisions that we make. Let's get started. Let's start with the problem definition. So I think this needs no introduction, so I'll go very fast over it. It's just we want to implement ideally a ideal functionality which has a class in it, and there's a set of clients. And the functionality samples random values and periodically outputs these values. We have seen this definition in the workshop today. And this is what we want to implement. And there are many applications, as mentioned earlier, randomized jury, consensus protocol, clinical trials, digital lottery, and also player drafting. Those are like general applications of randomized beacon, but we can also have applications in blockchain setting, which are MB protection, jury election, games, lotteries, and many more. I think, yeah, already repeated multiple times so far. So, but in blockchain, we often have some additional requirements from the randomness beacon protocol itself. So this is what I'll cover. So in many applications, we want randomness after every block. We want randomness to execute a randomized smart contract. Oh, I think there's an issue with my microphone. Is it?
It's slightly, yeah, like unstable, but it's okay. If you can improve it, that's better.
Okay, is it better now?
Yeah, it's better actually.
Okay. Oh, thank you, Arlene, for mentioning. Okay, so we want randomness for every block. And if this is the blockchain that we are running, so as soon as we generate a new block, we want to output a new random value Ri. But the natural question is, what is a good time to reveal this random value or the random coin? If I plot the time, let's say, and say this is the time we commit the block, then one option is to reveal the block random value early. But this is problematic because an adversary can now see the random value and can change its mind. So we don't want this. The other option is to reveal much later. We commit the block and then we reveal the random value. But this has other problems, like it will introduce additional latency in the blockchain pipeline. Now the smart contracts have to wait to get this random value. The ideal solution is as soon as we commit the block, we want to reveal the random value. And so the smart contracts can use it instantaneously. So in the talk, I will give an example where there is an additional one round of delay, but we have a very nice, very cute optimization that's already been deployed in Aptos where the randomness are almost instantaneous. So one option to get randomness in blockchain is to rely on an external source of verifiable randomness. such as DRAM, Chainlink. I think Supra will also have one. And this is how the whole system will look. So we have the blockchain, and as soon as we generate a block, the block will query the blockchain, will query the random, the external oracle will get a random value and use it. And we do this for every block. But there are two main issues. One is the security, is that now the security of the blockchain somehow depends on rely on the security of the external VRF. And also there's an usability issue, is that it's hard to get the beacon output timing right. The blockchain doesn't want to query too early or too late, because as I mentioned, this has other problems. So what we implement is that the blockchain validators will internally implement their own randomness beacon, and so that they can get the beacon output instantaneously as soon as they commit the block. So that's the design, one of the crucial design choice we made. So the cryptography tool that we use is a threshold VRF, or also the weighted VRF, which are verifiable random function. I think you have already seen this. For this talk, I won't make technical distinctions between VRF, verifiable and VUFs, which are empirical functions and unique signatures, but they're closely related, and you can get a VRF from a VUF. So the key tool in threshold VRF is the threshold secret sharing. And this is how it works. So it's a mechanism to share a secret S into n shares. Let's say we have a party that wants to share the secret into n pieces, 5 pieces in this example, such that any subset of t plus 1 shares reveal the secret, but a subset of t or less reveal nothing about the secret. And this is the classic example of Samir secret sharing. I think most of you have already seen, where we embed the secret as the constant term of low degree polynomial, specifically degree t polynomial, and each share is one evaluation point on this polynomial. And given this threshold secret sharing, we can construct the threshold VRF, and there is this beautiful threshold VRF by Boldereva based on Bonellin's Sacham signature scheme, BLS signature scheme. So I'll also cover this as a background on how this works. So let's look at the BLS threshold signatures. So we have a set of parties. These parties will run a key generation protocol or an idealized key generation protocol to get secret keys, where party 1 gets S1, it's a secret key, and some public key and threshold public keys. So party 2 will get S2, which is a secret key, and also the same public keys, and so on and so forth. And these secret keys are Shami shares. Recall the Shami shares on the polynomial of a random secret S. The public key is 0 to S, and threshold public keys are defined appropriately. We can also run a distributed key generation protocol to generate these keys. Now, once the parties have their signing keys, they can generate the VRF as follows. So each party locally computes VRF share, which is hashed as a message, which is the input to the VRF, and raise it to their secret key, SI. So every party will locally do that, and they will send this value to an untrusted aggregator. And the untrusted aggregator runs a public operation, computes a public function of this partial VRF shares, which is also called a Lagrange interpolation for those who are familiar with, and can compute publicly hash of the message raised to the secret S, whose shares are these SIs. And then the final VRF output is hash of the message raised to S. That's the VRF output. And these are some very nice properties. One is the VRF evaluation or signing process is non-interactive. Also, the partial signature size are constant, and the aggregation cost is also very fast, quasi-linear. And finally, BLS signatures are unique, and then thus we can use it as a VUF as well. Okay, so if we are given a threshold VRF, how to design a randomness beacon with just one message delay? So we have the blockchain that is running. And as soon as we commit to a new block, we can compute this function. I'll go into this function. So we hash the block, we take the block hash, and then evaluate the threshold VRF with block hash as the input. And then use that output of the threshold VRF as the random output. And we can do this for every block. And the properties from the threshold VRF properties, we get that the VRF computation will require a contribution from at least t plus 1 parties. Hence, an adversary cannot know the VRF a priori unless it corrupts many parties. And also, we can do it using just one round of communication because the scheme is non-interactive. And there are very nice properties where the security of the scheme is now as secure as the underlying blockchain itself. And so it only uses one additional round of latency. But again, I want to mention that we have nice optimization to get instantaneous, almost instantaneous beacon output. But the question is, are we done? Now, obviously, the answer is no. And it's because the proof of stake blockchains are weighted. And here's the setting. So we have a set of parties or set of validators. Each validator has their weights. I use WI to denote the weights. The underlying assumption of the blockchain is that validators of combined with at least at most 1/3 of the total weight are malicious. So we now no longer count the number of validators. We're now looking at the weight distributions of them. And these weight distributions can vary a lot. For example, in Aptos, as of March 2024, 880 million stake tokens are staked as part of the consensus protocol. And then 14 validators have staked more than 15 million, and then some a lot, 40, more than 40 has less than 1 million. So what I mean to say is that the weight distributions can also vary a lot. They can be arbitrary. To solve the randomness beacon problem in the blockchain setting, we will need the weighted VRF. So that's what we will try to construct. But before we give our own construction, let's look at this folklore virtualization-based approach. So where we have parties, and each party have their weights. These are I'm using the representative weights. Then we assign to each party a signing key proportional, the signing key proportional to its weight. Party 1 will have 1 signing key, party 2 will have 3 signing key because its weight is 3, and so on and so forth. And these are Shami shares of, let's say, 9,6. Just an example of a degree 6 polynomial where we are computing 9 shares. So these are weighted. So the total degree will be like proportional to the total weight. And then on input a VRF input, let's say the message M, each party will locally compute the partial VRF share. Party 1 will compute row 1. Party 2 will compute 3 VRF shares, 1 for each of its signing keys. And everybody will locally compute this. And then they will send these values to an untrusted aggregator. Untrusted aggregator will take all of them and combine them to compute the VRF output row. And this, the later part, can be a public operation. We can immediately notice some issues. That the per-party VRF evaluation cost is now proportional to the weight, both computation and sending. And aggregation is proportional to the total weight. And we also need a distributed key generation, which is proportional to the total weight. But I want to mention that we don't know how to solve all of these problems. We can solve partly, and then there are a lot of open problems that I'll discuss. So what's our approach? So I'll first describe our approach with pictures. So here's our approach. So we have parties, let's say again, with some representative weights. First thing we do, we are doing a normal virtualization. So we are creating a large polynomial, and let's say SI is shares of each party will get a multiple from these shares. But we don't assign these shares directly to each parties. Instead, we encrypt them. So we encrypt each shares. So we have S1 to S9. We'll get ciphertext C1 to C9. But we do this encryption in a very clever way. So for the first party, we sample a secret key K1. And then we encrypt the share S1. Let's say this gets us 1. The party has only 1 weight, so this is simple. For party 2, we use a single key K2. This is very crucial. We use a single key K2 to encrypt all the shares. And we get 3 shares, 3 and a ciphertext. And same for party 3 and party 4. Now, these parties, we will assign to these parties this K1, K2, K3, K4, not the individual shares. Encryption keys we use to encrypt these shares. And then to an aggregator, we'll give all the encryptions, all the ciphertext. Okay. Now, each party on an input message, it will compute a sigma, which is not its VRF evaluation share, but some function of its secret key and the message. And then every party will locally do that. And it's crucial that these are constant, the size of these are constant. And then they send these values to an untrusted aggregator. Now what the untrusted aggregator does, it has this ciphertext, which is a long vector, and it uses the short sigma with the ciphertext to compute the VRF evaluation shares by doing some public operations. The aggregator will do this for party 1, will also do it for validator 2, party 2, and so on and so forth. The aggregator now has this VRF evaluation share that it can compute publicly based on the ciphertext that it got and some partial values that each party computed, and then compute the VRF shares and compute the VRF output. So this is how our whole system works. But for the experts who are familiar with the functional encryption, so what we're doing here is exactly the functional encryption of the secret shares. If I look at the properties, so per-party VRF evaluation cost, both bandwidth and compute, is now constant. It's independent of the weight. But we don't get all the properties. The aggregation cost is now still proportional to the total weight, and also distributed key injection that we do is also proportional to the total weight. But we have a lot of really nice optimization in the second part to be able to handle virtualization. I'll talk about some of those a bit later. Let's look at some of the macro results, what we get in the Aptos Plexus. I think these results are a bit old. The numbers probably updated now. So if we run the DKG, so what we do, we cannot run anything with 880 million stake or shares. We do a rounding down, and then we get the total weight of about 4,000. The DKG takes about 64 seconds, and randomness takes about 200 milliseconds when we have this one additional round of delay. I think the latest numbers are probably 20 milliseconds when we add this later optimization that we have. The DKG is still virtualization based, which is a bit problematic, but it's okay in certain applications. In this application, because we have to run this DKG once every epoch, and we also make some design decision to make sure that the DKG doesn't become a bottleneck, which I'll cover later. And there is a very nice open problem to improve the DKG. Let's also look at some of the micro results. So if I look at the VRF evaluation per part, now it's independent of the total weight as expected. And it doesn't grow with the total weight or doesn't grow with the per part. And also VRF verification time doesn't grow with the total weight. And finally, the VRF share size is also independent of the total weight. But something does depend is the derivation time, which is which is how the aggregator computes the rows and individual row i's and then computes the row. That depends on the total weight. And our cost is higher than the BLS. It's because we are doing a slightly more expensive operation, the same number of operations, but more expensive operation. But if we look at the total aggregation time, which is to individually verify each value that each party computes and then derive, our total aggregation time is still better than BLS virtualization. And if the weights grow higher, we expect our gains to be much better. Okay, so now I want to give, since I have time, I want to give some of the concrete mathematical details that how our scheme works. But I'll show it first using an unweighted scheme, because the math is much easier to show, and then briefly show how we extend it to weighted setting. Okay, let's take this setting with 4 parties, and I'm assuming that the weights are 1 for now. So let's say we do a 4,2 Shamir shares. So we have 4 shares, and each share belongs to 1 party. And then we encrypt. How do we encrypt? The encryption here is this. So we have a group generator H, and we raise to the generator the multiplication of the secret key K and the secret share S. So we multiply these two and raise it to H. That's what we do for party 1. We do the same for party 2. We have the second key, which is K2. So the second share, we multiply those two and raise it to the exponent. And we do this for all parties. Now, each party will get their individual, the KIs that they receive. They don't get the shares. And then upon input a message, they compute their sigma i's as hash of the message raised to 1 over ki. That's very crucial. So each party 1 will compute hash of the message raised to 1 over k1 inverse. Party 2 will also do that. And this process repeats. Now, if I take the ciphertext that the aggregator will have, and we can combine this ciphertext with sigma i's to compute row 1. And how do we combine? We just pair these two. So now if we look at this pairing, we have h raised to k1, and we have hash of the message raised to 1 over k1. And once we do the bilinear pairing, the k1 in here and k1 inverse here will cancel out. And what we finally get is pairing of h with hash of the message raised to the secret share of the party. And we do the same process for every party. Again, K2 here will get canceled out with 1 over K2, and we get the star with you. And once we finally combine, we define the VRF output with the pairing of H with hash of the message raised to the secret S, which is what is shared here. This is how our construction works in the unweighted setting. Okay. So I also want to talk a bit about the verification case. So unfortunately, we don't know how to verify the final VRF output efficiently. So what we do in our case, we have to verify this individual sigma i's and then rederive rho. That's if you want it for a general application. But in our blockchain, things are slightly better because the blockchain external clients can rely on a weighted multi-signature on the final VRF output from the validators to trust the VRF output. And this doesn't have any additional overhead because this has already been done for the rest of the blockchain state. So we can include this VRF output also as part of the blockchain state. So let's look at how things work in the weighted setting. I'll just show it for a one party, assuming that party has weight 3. And so these S1, S2, S3 are shares of that party. Now we encrypt. How we encrypt? We have the key K1, and we use the same key to encrypt all the shares. So we raise H raised to K1 times S1, K1 times S2, and so on and so forth. The same key is used everywhere. And the party gets the key K. And upon on input a message, the party will compute a single value, which is hash of the message raised to 1 over K1. And on the untrusted, the aggregator, upon receiving this ciphertext, can compute this row as before. Pair the sigma 1 with the first ciphertext, we cancel K1 and we get pairing of H with hash of message raised to S1. And same for the second, we'll get S2 here, we'll get S3. So it's the same sigma value we can use, combined with multiple ciphertexts to compute the VRF shares of the party. And then the aggregator can combine all this, say, row i's to compute the VRF output. There's a very nice open question that I thought about a bit, but I don't know how to do it. As I mentioned, this all relates to the functional encryptions that you might have seen. So the open question is design similar functional encryption for BLS. I don't know how to do it. If you have some ideas, I'll be very happy to talk. So since now I want to briefly touch upon how we do the distributed key generation in our setting. So ultimately, our end goal is to run in a decentralized way. So let's look at how we do. So what are the system model and requirements? So we have this notion of time, which the blockchain is running, and the time is divided into epoch. So we have epoch I with a set of validators, and then we'll have the next epoch with a possibly different set of validators. Not the whole set will change, but a portion of those parties in the next next epoch might change. So what we pick a design where the validators of epoch I will generate the VRF keys for the validators of epoch I plus 1. And why do we adopt this? Because we adopt this for efficiency. Recall the DKG is virtualization based and it's expensive. So we don't want to stall the start of the next epoch. We want the previous I party to run the VRF keys for the next epoch in parallel to running the blockchain to have much shorter delay. So we do this using a two-step DKG protocol. So the first step is this. It's run by the previous validators for the new validators. Let's say these are the previous validators. They have their own weights. And we also have new validators with their respective weights. And they run a DKG similar to standard Shamir secret log-based DKG to get the generate keys for this new validators. The new validator will get H to the S1 as a secret key. Validator 2 will also get the appropriate keys, where the SIs are Shamir shares of a secret S. And then, in our case, we use a non-interactive DKG with a new aggregatable PVSS. We use non-interactivity to exactly for this property that the previous validators can run the DKG for the new validators. And we require an aggregatable PVSS for efficiency. It's crucial to support virtualization because some of the steps in our scheme are still virtualizations. So what happens in step 2? So it's run by the new validators. We have the new validators locally receive these keys from the previous validators, and they locally sample their key. Party 1 will sample key 1, K1, and then output the encryption. Party 2 will sample K2, also output this encryptions for the aggregator. So each party will do this. And then all these steps, I want to mention that are added with appropriate verifications. And finally, parties can delete their old secret, like linear size secret keys, and only keep this K1s as their final state. And the aggregator needs to store all the ciphertext. So this is what happens in the current design. Okay, I want to summarize here. So we designed a randomness beacon in the weighted setting. And the key idea is the weighted VRF or VRF with a constant signature size. And also we have in the paper new aggregatable PVSS and a DKG where we use this aggregatable PVSS crucially. The system is running in full-fledged in Aptos blockchain, and we prove the security assuming bilinear diffusion assumption. They're very nice open problems. One is to improve the DKG. So the secret key is now in group element because this functional encryption we have only works in the setting, designed it for field element style BLS, and also improve the aggregation cost and verification cost. That's it. That's all what I want to cover. Thank you so much.
Thanks a lot. Great talk. Lots of technicalities. I think you covered very nicely within relatively short time. I guess there will be definitely a lot of interest in this area, like a lot of innovations going on. So a couple of questions I see both are from Rohit Sinha. So is there a public documentation on how the stake is rounded down to shares?
Oh, I don't know this answer. Maybe Aline can respond to it. Yeah, I don't know.
Okay.
There are internal documents I know, but I don't know about the public. Yeah. But I think we are doing simple stuff.
We can maybe Aline can answer on the chat then, right?
Yeah.
On the chat, yeah. I guess anyone can answer, right? Probably we can only answer. I'm not sure if Aline is the co-host.
Oh no, you can or we can add him to the chat, or you can just mention on the chat.
Okay.
Yeah, wherever you mentioned the tag, we can post.
I want to address the second question of Rohit, that whether we are doing interpolation in the target group. We are not. So the number of target group operations we do are proportional to the number of validators. And we do the amount of work we do, which is proportional to total weight, is still in the source group. And the interpolation is intertwined between some target group operations and some source group operations. But the target group operations are fewer, only proportional to the number of validators.
Mm-hmm. So anyway, you have this, the final value is not verifiable because it's already in the target group, right?
Yes, yeah.
That's one of the limitations, I guess. Yeah.
Yeah.
That's probably the only limitation, yeah.
Yes.
So there are other questions actually. Sorry, you wanted to share something?
Lynn said it's the later part of the paper has rounding algorithm, I think.
I see. Yeah, I believe it's in the paper. Okay. Madi Sidakat, nice work. If I'm not mistaken, to avoid users storing linear keys, the aggregator now needs to compute linear pairings. How might this trade-off impact the current deployments? Also curious about what is the biggest weights in Aptos. Is this not super large? Then linear key storage looks more real. Actually, it's also like I had a similar thing. So you showed this weighted distribution, they are very different, or like something like 9999 versus 8888 kind of thing, like very fractional weights or something.
So to answer so note that we want to do this VRF evaluation very often, once for every block. So that's what we wanted to optimize, because each block is getting generated every second. We're not really care about the storage. Like, it's fine to store linear size keys. Each validator can store, but we want to optimize the amount of computation that each validator needs to do, and then amount of message the validator needs to send. We want those to be much smaller because we will have to generate this VRFs very often, once for every block, and block generation is very fast.
I see. I think he was also asking about what is the biggest weight in Aptos.
That I don't know. Yes.
Yeah. All right, I guess we can come back to it in tomorrow's panel where Aline is there. So
Yes,
I need
yeah.
to take note on this. We need
I
more
do answer one
discussion,
question,
so.
but which is, yeah, even I have the question I have been very like definitive. So I'll probably ping him. So the question is that as compared to state of the art Aptos, the Aptos before including the thing, and now you include that in your blockchain or SMR process, how much is the delay that got added in the process?
I think Jolun told me with our latest optimization of reducing a round, it's about 20 milliseconds. From the time block gets committed, from the time when we can start executing smart contracts that needs randomness. That's where 20 milliseconds is not much. Yeah. Yes. But that's I think again we have to confirm it with Jolun, and then Aline can possibly reassure us that's indeed the correct numbers.
Yeah. Sounds good. I think I'll take notes of this question so that they're surely mentioned in tomorrow's panel. Like, what's the size of weights, weight size, and I guess there are other questions as well. All right, then. So, shall we move to the next talk? Okay, thanks again, Sourav. Very nice presentation.
Thank you.
All right, so next we have Guru from UC Berkeley, and he's going to talk about Timelock encryption with silent setup. Guru, over to you.
Yeah. Let me make sure I have the right file. Okay. Can you guys see my screen?
Yes, perfect.
Okay, perfect. Cool. Okay. So today I'm going to be talking about Timelock encryption with silent setup. This is joint work with Sanjam, Dimitris, and Mingyuan. Okay. So what is Timelock encryption, right? The goal is to encrypt a message such that it can be decrypted by anyone after some point in time t. But semantic security should hold for your ciphertext for all times before that point. And today, what I'm going to focus on is building Timelock encryption, given some committee, but the committee is not going to engage in a DKG. There's going to be zero interaction between them, essentially. So something else we would want from Timelock encryption is to decrypt ciphertext when the time has come. The committee should not need to interact with each other. And moreover, we would also like the committee to be unaware of ciphertext that are created, right? Because if you think about standard definitions of threshold encryption, the committee sort of needs to operate on the ciphertext. But here we want a situation where the committee doesn't even know ciphertext exists. They'll broadcast something at each epoch, and the client should just be able to pick that up and decrypt ciphertexts. And also you might want things like guaranteed output delivery if you're doing things like voting or sealed bid auctions, for example. Okay. So what is the textbook solution for Timelock encryption, right? This is also deployed by DRAND, which is you take threshold Bonnet-Franklin IBE, and you can basically build Timelock encryption from that very easily. And it has really nice properties, right? So the public key is like super short. The secret key is just like a Shamir secret sharing of this field element. And you have like really short ciphertext as well, where it's like one group element and just the length of your message. And in each epoch, the committee is going to set ID to be the particular block number or the epoch number, and they're going to issue that ID secret key. And issuing that is also super efficient. It's just one group element per party. It's not all amazing because at the beginning, you need to engage in this DKG, which requires order n squared communication for each committee. And if your committee changes, you have to engage either in a transfer of your secrets protocol, which incurs similar communication complexity, or you have to do the setup all over again. And in fact, if you want to handle things like asynchronous settings, this becomes a lot more expensive, and you can only tolerate n by 3 corruptions. And moreover, one issue that sort of comes up is that the threshold is fixed at the time of setup. Some clients may want to trade off liveness for security. You don't want to redo the setup for all these different settings, right? And so today, what I'm going to introduce is silent Timelock encryption that handles all these nice properties. It's going to remove the DKG, be much more efficient in the asynchronous setting, and you can also choose the threshold that you want to encrypt to at the time of encryption, not during setup. Okay, so let me show some pictures to really highlight what I mean by silent Timelock encryption. So in what's basically deployed in DRAND is there's going to be this interactive setup, and this client is going to encrypt to this public key. And at the end of the setup, all parties also get shares of the secret key. And the public key is used, and you specify which time it needs to be decrypted at. And then when it comes time to decrypt, right? So the committee is going to essentially issue the IBE secret key corresponding to that block number or that epoch number. And each party just broadcasts like a partial decryption or a partial issuance, and these can be deterministically aggregated into sort of that epoch's secret key. And given that, you can decrypt all ciphertext. So you would just run over all ciphertext in the second function, and you can recover all messages. Okay, so what do I mean by silent Timelock encryption, right? We're going to completely get rid of all of this interaction. And each party is going to independently sample their own public key and secret key pair, and they're just going to broadcast it and maybe post it in some directory, right? And then they're just going to disappear. And these public keys can be aggregated into the group's public key using a deterministic function. And this public key is also going to be succinct, just constant sized. So now when a client wants to encrypt, he can do exactly what he did before. He just downloads this group's public key and specifies which epoch it should be decrypted in. And the sort of behavior of the committee in each epoch is also identical. They just issue these partial decryptions, and it's going to be non-interactive as well. Okay, good. So before I go into any technical details, I'm just going to give you an overview of how our protocol compares against the Bonnet-Franklin IBE. The public keys of the group is just this DKG, and then it's like super succinct. But in our scheme, each party has a public key that's proportional to the maximum group size. So each party has like O of n group elements as their public key, and you can aggregate them into a succinct public key, whereas the Bonnet-Franklin, you sort of had to do this DKG. The storage of each party is also just succinct. It's just one field element. The ciphertexts are constant size, but our ciphertexts are a bit larger. And the partial decryptions of these partial issuance, however you want to view it, is also identical. It's just one group element. When it comes to security, the Bonnet-Franklin IBE, you can reduce it to BDH, which is like bilinear Diffie-Hellman, whereas our construction needs to rely on these generic group models. Okay, so what was this prior work in removing these setups, right? There's this line of work on flexible or distributed broadcast encryption, where essentially you can imagine it as like threshold encryption, but with the threshold being 1, and there's no interactive setup. There was some work that also focused on adaptive thresholds. So there's like this interactive setup in the beginning, but you can choose the threshold for decryption at the time of encryption. And there was one work that did silent threshold encryption, which would also give you silent time lock puzzles. But they did this from indistinguishable obfuscations, far from practical. And there's one last line of work that I want to mention, which is silent threshold signatures. So these essentially were able to show that you can have non-interactive setup, but you can have succinct verification for silent threshold signatures. And actually, the previous speaker was actually one of the authors on the second paper. Okay, so now, okay, good. If you were given obfuscation, witness encryption, or like these TEs, right? Could you actually achieve this primitive, right? So I'm giving you the most powerful building blocks in crypto. Can you achieve silent time lock encryption? How would you do this? The idea is you would create sort of an obfuscated program. The easiest way to think of it is, let's say you have SGX, right? So it's going to have the secret key of the Bonnet-Franklin IBE just hardwired. Let's say it can sample its own secure randomness. And the public keys of the parties in the committee are going to be hardwired as well. And now what you're going to say is when you want to encrypt a message, you're just going to do the IBE encryption. But the decryption is a little bit different. So when you want to decrypt, you're going to supply to this obfuscated program some identity and signatures on this identity from the end parties. And now what you're going to say is, okay, the box is going to say, okay, if enough parties have approved the issuance of the IBE secret key for this particular identity, then I'm actually going to do it, right? So let's say it's some threshold T. So then it's going to output this IBE secret key for the identity, and you can just use that to decrypt all your ciphertexts, as we discussed before with the Bonnet-Franklin IBE. So this would actually achieve silent setup because these public keys can just be sampled independently. Okay, good. Using a very similar idea, you can build silent time lock encryption using witness encryption as well. So what is witness encryption? The idea is you can encrypt to a statement X, and you can decrypt if and only if witness W such that the relation is satisfied. Okay, so what kind of witness or what kind of statement do I want to encrypt to, right? So can we build silent threshold or time lock encryption given witness encryption? So you can actually just get silent threshold encryption if you encrypt to some random string. I'm going to call this tag. And the statement that you would want to encrypt to is you can decrypt my ciphertext if and only if you know T signatures from any subset of n parties on this string tag. In this, all the parties would sample their public keys independently run, think any signature scheme, and you would encrypt to this particular statement. And to decrypt, parties just have to sign the ciphertext in some sense, which is signing this random tag. And if you just set this tag to be the epoch number and the committee just signs consecutive epoch numbers, then you can also just get time lock encryption. Okay, so I haven't told you anything. I've just told you can use the most powerful tools in crypto to get silent time lock encryption, which is not surprising. But the surprising part about this whole thing is that you can actually build a concretely efficient witness encryption scheme for a very specific language, where essentially you set these signatures to be BLS signatures. And that's what the rest of the talk is going to be about. Okay, So before I talk about what we actually did, I first want to introduce a compiler for witness encryption. And you can use this compiler on any NP relation which has linear verifiers. I'll talk about what I mean by linear verifiers in a second. People have probably seen this already, but let's recall pairing product equations. It's essentially equations where you just have a bunch of pairings and you're adding them up. And on the right-hand side, you have some target group element. That's all a pairing product equation is. So take your NP relation, right? And what I want you to do is express the verification circuit for this NP relation, which is, it's going to take in the statement and the witness. And let's assume the statement and the witness are group elements as well. And what you're going to do is express this verification circuit for this relation as a set of pairing product equations. So let's say there's a bunch of them, right? So they're going to look like this, where there's three types of terms, essentially. So the first type of term is where a statement element gets paired with another statement element. The second type of term is where a statement element is going to pair with the witness element. And the last type is where a witness gets paired with a witness, right? I'm going to say that this pairing product equation is linear if the degree in the witness is 1, which means no witness element is going to get paired with another witness element. So you've expressed the verification circuit for this relation in this form, and no two witness elements get paired with each other. Okay. And if you can express your verification circuit in this form, then I claim that I'm going to define the NP relation to have a linear verifier. And I'm going to describe the compiler in just a second, which will allow you to take any NP relation which has this form and build a witness encryption for it. Okay. So more generally, you can express these pairing product equations as in this matrix times vector form. So think in this entire talk, the blue text is going to be part of the statement and the red text is going to be the witness. Okay, oops, sorry. What does the verification circuit for some NP relation look like, which has a linear verifier? You can take a matrix of these statement group elements, and then you're going to pair them up with this witness. So this circle is going to denote pairing. And for the moment, just assume symmetric pairing, and it's going to make everything easier. And the C1 to CUs are the right-hand side of the pairing product equation. Okay, good. If you had this structure, how would you actually encrypt to the statement, right? So what you're going to do is sample a bunch of random field elements. And you're going to take, so this dot I'm going to denote by scalar multiplication. And what you're going to do is take a random linear combination of your of the rows of your matrix. And what that's going to give you is like V group elements. So think of this as just matrix times or a vector times matrix. And that's what you're going to arrive at here. And you're going to take the right-hand side of this equation and take the same alpha 1 to alpha u, which are random scalars, and exponentiate them with these target group elements. And that's going to become your encapsulation key. So for now, you could just think of it as masking your message with it, but you could also put random oracles, do key derivation, whatever you want to. Okay. If you have this sort of structure, the ciphertext contains V plus 1 group elements. Now, how do you actually decrypt this, right? All you need to do is observe that if you can compute a valid witness for this statement, then you can just take these V group elements that you had here and just pair them up coordinate-wise with the witness and just squish them. And you would effectively recover the right-hand side of the equation. And then once you compute this mask, which is also the encapsulation key, you can just subtract it out from your ciphertext or the second part of your ciphertext. Okay, so that's how encrypt and decrypt. Now that we have this framework, right? It turns out it's just sufficient for us to build a succinct linear verifier for the statement, which I mentioned earlier, which is I know signatures from T out of N parties on some tag, which is just a random string that the encryptor samples. Okay, good. So as a warm-up, let's do just like N equal to 1, and we're effectively going to recover the Bonnet-Franklin IPE. What do you start off with, right? You start off with the BLS signature. And the public key is just like this secret key, which is like a field element times the group generator in G1. And then the signature is just a hash of the message multiplied by the secret key in G2. And when you want to verify, all you have to do is pair the generator with the signature. And on the right-hand side, you pair the public key with the hash of the message. Okay. So if you just stare at this equation, note that if the statement contains the public key and the message, then the witness is just the signature, right? And this indeed has linear verification because no witness element is multiplied with another witness element. Obviously, there's only one witness element. So when you run our compiler, you essentially get two parts of the ciphertext. So the first one is you just take this generator and raise it to some random power alpha. And you can raise the right-hand side of the equation to the same power alpha and use that as your encapsulation key. To decrypt, note that if you just come up with a signature sigma on the message M, then you can just pair it with the first part of the witness encryption and recover the second part of the witness encryption and just subtract it out. Okay, good. So now let's come to our scheme, right? Which is actually how do you get it for threshold. So let's recall that we want to do succinct linear verification for the following statement, which is given a tag and public keys of the end parties. These are going to be in a statement. I want to prove to you that I know T signatures, sigma I, such that each of these signatures verifies under the respective public key on the message, which is corresponding to this string tag. Okay. So note that if all you cared about was succinct verification, it's really easy. You just have to throw a snack at it, right? And you'll get succinct verification. But the verification here is not going to be linear. And in fact, it's not reasonable to hope for that, because if you did get that, then you would get witness encryption for all of NP. But on the other hand, these two works that I mentioned earlier, which were doing the silent threshold signatures, actually give an efficient black box construction. But unfortunately, they're not linear either. But one could hope to make these constructions linear. And if you do, then you can just apply the compiler that I described earlier and get witness encryption for the statement, which would give us all these nice properties of like, so all these nice constructions of silent threshold encryption and silent time lock puzzles and so on. Okay, so I'm going to begin by recalling hints, which is one of these papers. Okay, so first, let me go over something called aggregate BLS signatures, which many of you might have seen before. And so the goal is to verify that a message has been signed by n parties. Now there's no threshold or anything. You just want to check that everybody has signed this message. So the naive way of doing it is you're going to run the verification algorithm on each of the signatures created by the parties. And this is fine, but this would require O of n pairings. People propose this optimization, which is you can just add up all the signatures and add up all the public keys. And then you only have to do one pairing, but O of n group additions. And importantly, you can actually take any non-trivial linear combination. So here I've just added things up, but you can just take any non-trivial linear combination. By that, the coefficient should be 0. And if you do this, you can still get the same guarantees of unforgeability and so on. And this particular property, which is the fact that you can take any non-trivial linear combination, will become important later on when we try to linearize things for our witness encryption. Okay, good. So we know what aggregate BLS signatures are. And okay, so what did hints and the other work as well do? Essentially, they said, okay, you can succinctly check that a message was signed by T out of n parties, by succinct like constant time. So note that if you had this oracle, which would guarantee to you that the public keys were already aggregated correctly of these n parties, then all you need to do is just verify a single signature. And then this is constant time. So note that it's sufficient to prove now if that this aggregation was done correctly. And if that proof has constant time verification, then your overall protocol has constant time verification. So what are the equations that sort of get proved in this hints protocol, right? There's three things. So the first one is you prove that, okay, I did take some BI, which is a coefficient, and I added the public keys with those coefficients, and I got this aggregated public key. And I also proved to you that the number of non-zero BI, or the sum of these BIs is larger than T, and that each of these BIs is binary. So if you can prove these three things, then you've ensured that at least some T size subset was chosen and then aggregated. And now I've verified that the signature, and then all I need to do is check that the signature verifies under this APK. Okay. So the way they do it is by using the univariate sum check. And essentially, okay, so what is a univariate sum check? So the idea is if you're given a commitment to some polynomial f of x, you can prove that the sum of evaluations of this polynomial on some domain H is equal to some little s. And the idea behind the univariate sum check is that it's sufficient to show that there exist two quotient polynomials, q1 of x and q2 of x, such that this equation is satisfied. It's not really important how you arrive at it and so on, but just believe me for now. And then you have some degree checks on these guys as well. So if you just stare at this three equations, right? Note that, again, in this first equation, maybe it's not very obvious, but no two red elements is paired with another red element. And these red elements are going to form the witness in our witness encryption scheme. Verification here is linear, so the univariate sum check is already linear for us. Okay, good. So now how do you prove that the aggregation of public keys was done correctly? Or how did hints do it? So what they said was, okay, let's put the public keys on a polynomial, right? Think of the x coordinate as being the party's index I, and you put the public key sort of on the y-axis. And then you're going to interpolate in the exponent. And then what you're also going to say is, okay, I have my selector polynomial, which are these BIs. So it's either going to be 0 or 1, depending on the party signing or not. And I'm going to interpolate a selector polynomial B of x. And what this gives us is, oh, sorry. And then they're going to run a sum check on the product of these polynomials, pk of x times b of x. And if you look at the what comes out of this, it's essentially an aggregation of the public keys for the parties that did actually sign. So this APK is going to be the little s for the sum that pops out. And you prove that b of x, q1 of x, and q2 of x, such that all these properties are satisfied, the degree checks. Okay. So if you want to actually compute these quotient polynomials, you need some additional terms, which are known as these hints in the exponent. But verification doesn't actually need this. And so this is why the public keys are large. And the details are not important for the talk, but just note that this equation is linear because no two red elements are getting multiplied with another red element. Okay, good. Okay, so this is what hints did, right? It proved that this aggregation was done correctly, and then you can prove that the weight of the aggregation was sufficiently large and that each of these coefficients was binary. So we showed that this first equation was linear. The second equation is linear. You just make this an equal to, and then you're done. But the third equation, you can just see, just from staring at it, that you actually need a quadratic constraint here. And that is what hinders us from directly compiling out hints to get what we need. And then is there a way to fix this? Can we make this check linear and still retain soundness and so on? And if you recall from this property that we observed in the aggregate BLS signature scheme, the coefficients didn't have to be binary. They could just be 0 and non-zero, where 0 is for the parties that didn't sign and non-zero for any party that signed. And you would still retain the guarantees of unforgeability and so on. So let's get rid of these two equations and replace it with something else. And I'm going to call this the modified hints protocol, where you just prove that there's sufficiently many non-zero BIs in this summation, right? So now the hope is that you could prove this second constraint using linear verification. Okay, good. So let's go back to how we were proving the aggregation was done correctly, right? So you had this polynomial pk of x and this selector polynomial b of x, and you would prove that the degree of b of x was sufficiently low, and you would just run some check on this public key polynomial times the selector polynomial. Instead, what I'm going to say is, okay, now the prover can actually choose arbitrary coefficients of their choice, right? Where instead of forcing them to choose the
Hi,
sign...
Guru, just to confirm, so I think we are running short on time. So
okay.
you can
maybe wrap up in a couple of minutes would be good.
Sure. Yeah. Okay. So I'm going to let these parties choose whatever coefficients they want. And now I claim that this polynomial b of x has at least t non-zero points if I can prove that the degree of b of x is at most n minus t. And this sort of follows from the Schwarz-Zippel lemma because you have n points and the degree of the polynomial is n minus t, so you can have at most n minus t zeros. Or it could just be a zero polynomial, but there's an easy way to fix that where you introduce this dummy party, which sort of always signs. And now if you just compile this out, you're done. You can just run the compiler that I described in the beginning. Everything is linear at this point, and you actually get this nice witness encryption scheme. Okay, so we showed that both of these constraints are actually linear. And now let me quickly go over the evaluation. The keygen is expensive because you have this, okay, so it's unoptimized and it takes quadratic time, but if you pre-process the Lagrange coefficients, you could do it in linear time. Okay, encryption takes less than 7 milliseconds, partial decryption takes less than a millisecond, and reconstruction takes about 130 milliseconds with 512 parties. But I want to note that most of this is computing the witness. So if you want to decrypt many ciphertext as you would do in Timelock encryption, this is a one-time cost and the incremental cost is just a few milliseconds. Yeah, so the code was in the last slide, sorry. And this is a link to our paper and there's also a blog post. Thanks for listening.
Okay, nice talk. It's a bit technical in the end, but so I have a question. So I think you mentioned that there was some approach because from Sourav's talk, right? So about this weighted VRF and from this silent encryption, there might be a possibility there. Can you elaborate more on that?
To build
putting thing in the,
okay. So
I
one
mean,
thing I realized
putting thing in the context, like within this context of this session, actually.
Right.
Yeah.
Sure. Yeah. So one thing I realized was that if you do VRFs with silent setup, then you actually get non-interactive key exchange, which there's black box impossibilities. So I think if you really wanted weighted VRFs, you would need to pay the interactive setup. And yeah, I don't see a way around it, at least from when we had discussed last time. Yeah.
So do you have a formal statement for this? So that
Yeah. So if you have a silent
yeah.
setup with, let's say, not even weighted VRF, let's say you have a silent setup VRF, right? So what this means is you can agree on like randomness non-interactively. And if you just set the threshold
Sure.
equal to 1, then you just get non-interactive key exchange, which we know is difficult to achieve, at least in with black box constructions.
And that would be different from PRF. So because PRFs are not maliciously secure. VRF offers verifiability.
Yeah. Good. So even with the, I think even without verifiability, you would, yeah, you're right. So even without verifiability, I think this would imply it. So the silent VRF is a much more stronger primitive than what you would need for multi-party.
Interesting. So that means like having this deterministic requirement on top of the silent signature is a big deal. Wow, that's
exactly.
pretty
You're getting
surprising.
deterministic output. Exactly.
Okay.
And the reason we can get deterministic is because you have like randomness coming in from the encryptor. But in VRF, you don't have any source of randomness except the parties.
Okay, that's quite an interesting fact actually. Okay, thanks. Okay, any other questions? I think Aline has a comment that PKs are typically group elements while polynomial evals are field elements. So how do you put PKs in the polynomial? I guess you put the S. Do you see it in a Q&A?
There's a Q&A. Okay. My bad. Yeah, okay. So public keys are typically group elements while polynomial evaluations. Okay. Yeah, good. So this is why you need the hints, which is this long public key. So think of it like getting the secret key times powers of tau. If you have all the powers of tau times the secret key, then you can actually do all interpolation and so on in the exponent. The details are you have to sit down and work them out, but you do pay this price of a larger public key simply because of that, because you want to do everything in the exponent. In the aggregation phase, which operations depend on the number of signers and which operation? Oh, okay, maybe this
is for the previous one. Yeah, I think we missed this because the weird thing about Zoom is that because if you're a co-host, you cannot ask the question, you can only answer. So that's why Pratik probably pasted and we just overlooked. But I guess like we can ask directly to Sourav at some point, or maybe Aline as well in tomorrow's panel. Yeah. All right. Thanks a lot, Guru. So final talk of today, it's by Kay who is an assistant professor at University of Michigan. And this is actually super exciting stuff, like game theoretically fair randomness generation. We internally thought about using game theory and how to do it within this context of randomness generation. I'm very excited to see that finally a sort of a technical talk on this topic. Okay, Key, please, over to you.
Thank you, Pratik. Can you see the slides clearly and can you hear me?
Perfect. Yeah. Okay, please go ahead.
So, yeah. Hello, everyone. I'm very happy to be here and share this line of our work about game theoretic fairness. And this is based on a line of our previous work. And feel free to post your question in the channel if during any time of the talk. Okay, so let's imagine next year we'll hold this workshop in person. So Aniket and Pratik needs to decide what to eat during the break. Aniket prefers sushi, but Pratik prefers cake. None of them can persuade each other, so they decide to toss a random coin. Since this is a Web3 workshop, they decide to do something cool. If the output is 0, we will have sushi next year, and otherwise we will have cake. So what they're gonna do, they're gonna use the Blom's coin toss. They will first each post a commit to a random bit and post the commitment to some public bulletin board, for example, blockchain. After that, they each open their commitments and reveal the random bit inside. Let's say Aniket bit is 1 and Praday's bit is 0. The outcome is just the XOR of these two random bits. So next year, we will have cake during the break. However, Aniket is super smart, and he's a strategic person. He can wait for Praday to first open his bit. It's 0. So now Aniket knows that if he opens his commitment, he's going to lose the game. So what if he refuses to open? Then in this case, we just say, okay, Praday, you just automatically win. And we will still have cake next year. So here, even if any key doesn't follow the protocol, he cannot gain any benefits. This protocol sounds good. It solves our problem. So formally, in a coin toss protocol, our goal is to toss a uniformly random coin. And specifically, we care about two properties. Correctness. If everyone behaves honestly, we hope to get a uniformly random coin. And second, fairness. The notion considered in classical cryptography literature is usually referred to strong fairness, where we require that a player cannot bias the output towards any direction by deviating. Unfortunately, this was proved to be impossible by Cleve in 1986 against half or more corruption. When there are two players tossing the coin and one player can deviate, it is impossible to design a polynomially many rounds strong fair coin toss. Even in the Blum's coin toss protocol we just saw, any kid can always bias the coin towards one by intentionally losing the game. But a rational player would not do this. Instead, Blum's coin toss protocol actually achieves a weaker notion of fairness, a game theoretic flavor of fairness. There we saw that even if Aniket doesn't follow the protocol, he cannot increase the probability of him winning the game. So basically, it achieves a game theoretic fairness, which guarantees that a strategic player cannot benefit themselves by deviating from the protocol. This notion was first formally proposed by Chong et al. In their 2018 work at TCC. So now we've seen a game theoretic fair protocol for two-party coin toss. What about multi-party coin toss? In multi-party coin toss, many players get together to decide a uniformly random coin. Here, every player has a publicly known preference, and we call those who prefer sushi as sushi supporters and those who prefer cake as cake supporters. Now, at the end of the protocol, we get an outcome, which is either sushi or cake. If the outcome matches a player's preference, then it gets utility 1. Otherwise, it gets utility 0. In a multi-party coin toss, some of the players may form a coalition, and their goal is to increase their joint utility, which is the sum of every coalition member's utility. For example, if the outcome is cake, then this coalition gets utility 3. And if the outcome is sushi, this coalition gets utility 2. As with two-party coin toss, in multi-party coin toss, we care about correctness, which says that if everyone behaves honestly, then the output should be uniformly random. And now game theoretic fairness is defined with respect to a coalition. We require that a strategic coalition should not be able to increase its expected joint utility by deviating compared to honest behavior. So basically, game theoretic fairness guarantees that the honest protocol forms a Nash equilibrium where everyone is incentivized to follow the protocol honestly. So one question you may have is, why should we care about this game theoretic fairness? Why not just stick to strong fairness? In every talk we've seen today, we have seen that randomness is widely used in many decentralized applications, lotteries, leader elections, online games, and in all these applications, we do want to achieve fair randomness. Unfortunately, strong fairness is only possible if we have honest majority, but in many decentralized applications or in some of these online games, we may not always have honest majority. It is possible that an adversary creates many pseudonyms and control a majority number of pseudonyms running this small task, which requires the randomness. Such kinds of attack has happened before where there are people like creating many pseudonyms to deduce value from the Solana blockchain. So we do want to achieve some meaningful fairness against majority-sized coalition. So this is why we care about game theoretic fairness. Now you may ask, okay, then is it possible to achieve game theoretic fairness against majority-sized coalition? We've seen that for two-party coin toss, Blum's coin toss protocol achieves game theoretic fairness against one corruption. But what about multi-party coin toss? On one hand, we know that if the coalition size is less than half, if we have honest majority, then we can achieve strong fairness by standard multi-party computation techniques. And on the impossibility side, Previous work by Chong et al. Showed that it is impossible to achieve game theoretic fairness against a -1 sized coalition if each outcome has at least 2 supporters. But the whole middle space is unknown to us. So we ask this question: under what size of a coalition is it possible to achieve game theoretic fairness? Exactly where should we draw this line between feasibility and a line of my previous work explored game theoretic fairness for different randomness generation tasks. For binary coin toss, we give a protocol that achieves game theoretic fairness against corrupted majority, and we proved it optimal. We also showed that there is no game theoretic fair coin toss protocol that tolerates T+1 sized coalition, where this T is the size of the coalition our protocol can tolerate. Later, we also extend this to a more general task where players want to together sample some randomness from any given distribution. And here we give a nearly optimal protocol against majority-sized coalition for arbitrarily efficiently sampleable distributions. I do want to emphasize here that for game theoretic fairness, you cannot just get randomness from arbitrary distribution by simply composing uniform randomness with the standard composition like rejection sampling. This is very different from strong fair coins. And in addition, we also explored leader election tasks where we give a log star around approximately fair leader election protocol against 90% corruptions, where approximate fairness means that the coalition can gain a little bit, but not too much more utility compared to honest behaviors. And in addition, I do want to emphasize here that all our protocols achieves public verifiability. So anyone who looks at the transcript can verify the correctness of the output. So all these results imply that game theoretic fairness is indeed possible and gives us some interesting protocols against corrupted majority, which was impossible under strong fairness. So in the rest of this talk, we will mostly focus on binary coin toss. I will first show you a toy protocol for 2 sushi supporters and 2 cake supporters, which achieves game theoretic fairness against coalition of size 2. Since previous work showed that this, for such kinds of when we have 2 sushi supporters and 2 cake supporters, it is impossible to achieve game theoretic fairness against coalition of size 3. This is optimal. And I will probably mention just a few words about how to generalize this idea. And I will show you an illustration of the landscape, which is very different from that of strong fairness. So now let me show you that toy example. Let's say we have 2 sushi supporters and 2 cake supporters. So this protocol is quite simple. Each group just first do a Blom's coin toss within their own group to elect a winner. Let's say it's Aniket and Praday. Now these 2 winners, they again run a Blom's coin toss protocol to decide the final outcome. Very simple. And now let me explain why it satisfies game theoretic fairness against any 2-sized coalition. First, if this coalition contains 1 sushi supporter and 1 cake supporter, then this coalition actually has no difference of the outcome. No matter what is the outcome, their utility is always 1. So there's no way they can increase their utility. If the coalition contains 2 sushi supporters, then of course they can decide who is the winner. But they cannot increase the probability of them winning in the second round of Blom's coin toss protocol, because we have seen that Blom's coin toss satisfies game theoretic fairness. So this coalition cannot increase the probability of getting a sushi outcome. So they cannot benefit. And the same works for a size of 2 coalition containing the 2 cake supporters. So this protocol is extremely simple, and it achieves game theoretic fairness against 2-sized coalition. Let me briefly mention how to generalize this idea. The structure is similar. We just let the sushi supporters together decide a coin C0, and let the cake supporters together decide a coin C1. The outcome is just simply the XOR of the 2 coins. And how to choose the coin for each group, how to deal with the case where one group actually fails to generate a coin, and how to deal with non-malleability issue is much more involved. Roughly speaking, we use multi-party computation with identifiable board to instantiate a specific form of verifiable secret sharing among a group to generate the coin, and we use cert. And if, for example, if C0, who generates the coin first, fails to generate the coin, we just use C1. And if C1, the cake group, fails to generate the coin C1, we will directly output sushi as a punishment. Due to the time limit, I will not go into the details of this full protocol, but instead, I want to show you the landscape directly. Can you see this plot?
Yes.
We can see that, and it's moving as well.
Here, the x-axis is the number of sushi supporters, and y-axis is the number of cake supporters. Without loss of generality, we assume the number of cake supporters is at least the number of sushi supporters. So here, and this z-axis is the size of the coalition. This blue, or let's a little bit purple plane, is half of x plus y. So this blue plane is the landscape for strong fairness. And this red plane, actually, we can see that it actually consists of two planes with a smooth transition in between. This red plane is the landscape for game theoretic fairness. Above this red plane, it is impossible to achieve game theoretic fairness. Between this red plane and the blue plane, we can achieve game theoretic fairness, but not strong fairness. And below this blue plane, we can achieve strong fairness. So from this plot, we can see that for game theoretic fairness, not only the size of the coalition influences the achievability, but also the relationship between the number of sushi supporters and the number of cake supporters largely influence the feasibility. That's why we actually have a phase transition here. And just for reference, I gave the formula here of the size of the coalition we can tolerate in the slides, just for if anyone is interested in checking. To wrap up, we explored this game theoretic fairness, which captures the incentive of the players. Basically, it guarantees that any strategic coalition, especially majority-sized, they cannot gain benefit by deviating. And we also showed that we can indeed achieve game theoretic fairness against corrupted majority, and the landscape is very different from that of strong fairness. I think there are some interesting open questions left by this line. And so the first, most related one is really, how do we make this game theoretic fairness practical? Our protocol runs in constant rounds against semi-malicious coalition, but it requires MPC with identifiable board and some resampling against malicious coalition. So it will be interesting to see if there is a way to reduce this run complexity or communication complexity with probably stronger assumptions to make it practical or even deployable. And another interesting direction is that in this talk, we've seen that introducing incentives circumvents fundamental impossibilities in cryptography. So can we introduce incentives in other cryptographic primitives that have been deployed in decentralized applications to achieve better results? Because we know that cryptography usually assumes a worst-case adversary, but in decentralized applications, especially on blockchains where currencies are involved, people do have incentive there. Adversaries do attack or deviate to gain benefits. Can we incorporate this in constructing our cryptographic primitives to get better constructions? I think this is a very interesting direction. So I'll stop here.